A policy involving thorough electrical safety inspections, particularly when replacing or modifying existing electrical services, is generally a good practice for several reasons. Firstly, a thorough inspection of all aspects of the electrical service, including the water ground rod, branch circuit protection, and other components, allows identification of potential safety hazards and ensures the system meets current safety standards. Secondly, not requesting an arc fault circuit interrupter, abbreviated as FSI, during a service change may help reduce confusion and ensure the inspection focuses on the specific scope of work, as FSIs are not always required for all types of electrical service changes. Thirdly, many electrical codes, such as the National Electrical Code, abbreviated as NEC, require thorough inspections of electrical services after modifications or repairs, and this policy helps electricians comply with code requirements, providing a higher level of safety. Fourthly, documenting the comprehensive inspection of the service, including the specific components checked, provides a clear record of the work performed. This record proves valuable for future reference and demonstrates the diligence taken to ensure electrical safety. However, it is important to note some potential limitations of this policy. One potential limitation is oversight of FSIs. If FSIs are not specifically requested or inspected, there may be safety concerns if the existing service requires FSI protection. Another potential limitation is an incomplete inspection. The policy does not explicitly mention the inspection of the electrical panel, wiring, and other critical components of the service. These areas may need to be inspected if they have been affected by the service change. Overall, while the described policy is generally considered a good practice, it should be implemented with a thorough understanding of electrical codes and the specific requirements of the service change being performed. Considering both the benefits and limitations, electricians can ensure effective and safe electrical inspections. When assessing the safety and compliance of an electrical service, various components and factors must be carefully examined. These include the grounding system, bonding, overcurrent protection, wiring methods, and adherence to the National Electrical Code, abbreviated as NEC. Grounding ensures a lower impedance path for fault current to return to the source, facilitating the operation of overcurrent devices. The grounding electrode system typically consists of a ground rod, metal water pipe, or concrete encased electrode. The resistance to ground should be verified to be 25 ohms or less, as per NEC section 250.53. If the resistance exceeds 25 ohms, an additional electrode is required. Bonding connects all non-current carrying metal parts together, creating an electrically conductive path. This includes metal enclosures, raceways, and equipment frames. Proper bonding minimizes voltage differences between these parts, reducing the risk of electric shock. NEC section 250.92 details the requirements for bonding service equipment. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect circuits from overloads and short circuits. These devices must be properly sized according to the ampacity of the conductors they protect. NEC Article 240 provides detailed requirements for overcurrent protection. Branch circuit protection ensures that each individual circuit within the building is adequately protected. The size of the circuit breaker or fuse should match the ampacity of the branch circuit wiring. For example, a 15 amp circuit typically uses 14 American wire gauge, abbreviated as AWG wire, and a 15 amp breaker, while a 20 amp circuit uses 12 AWG wire and a 20 amp breaker. Wiring methods refer to the types of cables and raceways used to install electrical circuits. Common wiring methods include non-metallic sheathed cable, also known as Romex, electrical metallic tubing, abbreviated as EMT, and rigid metal conduit, abbreviated as RMC. Each wiring method has specific applications and installation requirements. NEC Chapter 3 covers wiring methods and materials. The electrical panel, also known as the load center, serves as the distribution point for electrical circuits within the building. The panel must be properly sized to accommodate the connected load and have sufficient overcurrent protection devices. The panel should be inspected for any signs of damage, corrosion, or overheating. The service entrance conductors bring power from the utility company to the building's electrical system. These conductors must be sized according to the calculated load and protected from physical damage. The service entrance conductors typically terminate at the main disconnect, which allows the entire electrical system to be energized. The National Electrical Code, abbreviated as NEC, is a widely adopted standard for electrical installations. Compliance with the NEC ensures that electrical systems are installed safely and correctly. The NEC is updated every 3 years to reflect changes in technology and best practices. Arc fault circuit interrupters, abbreviated as SICE, are designed to protect against arc faults, which are a common cause of electrical fires. SICE detect the unique characteristics of arc faults and interrupt the circuit, preventing a fire from starting. SICE are typically required in branch circuits that supply bedrooms and other living areas. Ground fault circuit interrupters, abbreviated as GFCIs, are designed to protect against ground faults, which occur when current leaks to ground. GFCIs detect ground faults and interrupt the circuit, preventing electric shock. GFCIs are typically required in wet locations, such as bathrooms, kitchens, and outdoor areas. When performing an electrical inspection, it is essential to use appropriate test equipment to verify the safety and functionality of the electrical system. Common test equipment includes a multimeter, circuit tester, and ground resistance tester. A multimeter can be used to measure voltage, current, and resistance. A circuit tester can be used to verify that circuits are properly wired and grounded. A ground resistance tester can be used to measure the resistance of the grounding electrode system. Furthermore, consider the age of the electrical system. Older homes may have outdated wiring and equipment that do not meet current safety standards. In such cases, upgrades may be necessary to ensure safety and compliance. Aluminum wiring, commonly used in homes built in the 1960s and 1970s, can pose a fire hazard if not properly installed and maintained. Special precautions must be taken when working with aluminum wiring, such as using approved connectors and antioxidant compounds. Knob and tube wiring, an older wiring method, is often found in older homes. Knob and tube wiring is ungrounded and may have deteriorated insulation. It is generally recommended to replace knob and tube wiring with modern wiring methods. The demand load calculation is essential for determining the appropriate size of the electrical service and the capacity of the electrical panel. The demand load calculation takes into account the connected load of all electrical equipment and appliances, as well as any applicable demand factors. The calculated demand load is used to size the service entrance conductors, overcurrent protection devices, and electrical panel. Electrical safety is paramount. Always to energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not qualified to perform electrical work, hire a licensed electrician. Regular maintenance is crucial for maintaining the safety and reliability of an electrical system. Inspect electrical panels, wiring, and devices regularly for any signs of damage, corrosion, or overheating. Replace any damaged or worn components promptly. Keep electrical panels and equipment clean and free from obstructions. Furthermore, consider the impact of energy efficiency on electrical system design. Energy-efficient appliances and lighting can reduce the overall electrical load and save energy. When upgrading electrical systems, consider using energy-efficient products that meet current standards and regulations. Surge protection is also an important consideration for protecting sensitive electronic equipment from voltage spikes and surges. Surge protective devices should be installed at the service entrance and at individual equipment locations. Regular inspections of surge protective devices are essential to ensure they are functioning properly. In addition to the technical aspects of electrical inspections, it is essential to communicate effectively with homeowners or building occupants. Explain any findings clearly and concisely, and provide recommendations for necessary repairs or upgrades. Answer any questions they may have and address any concerns they may raise. It's vital to maintain detailed records of all inspections and repairs, including the date of the inspection, the findings, and any corrective actions taken. These records can be valuable for future reference and can help demonstrate compliance with applicable codes and regulations. Also, ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the National Electrical Code, abbreviated as NEC, and other applicable standards. Hiring qualified professionals helps ensure that the work is done safely and correctly. Stay up to date with the latest electrical codes and regulations. The National Electrical Code, abbreviated as NEC, is updated every 3 years, and it is essential to be aware of any changes that may affect your work. Attend training courses and workshops to stay informed about new technologies and best practices. Understanding voltage drop is crucial for ensuring that electrical equipment receives the proper voltage. Excessive voltage drop can cause equipment to malfunction or overheat. Voltage drop calculations should be performed to ensure that conductors are properly sized. Also, be aware of the specific requirements for different types of occupancies. For example, healthcare facilities have unique electrical requirements to ensure patient safety. Industrial facilities may have specific requirements for hazardous locations. Finally, prioritize safety in all aspects of electrical work. Electrical work can be dangerous, and it is essential to take all necessary precautions to prevent accidents. Follow safe work practices, use appropriate personal protective equipment, and always de-energize circuits before working on them. Grounding electrode conductors connect the grounding electrode system to the electrical system. These conductors must be sized according to the size of the service entrance conductors. The grounding electrode conductor should be installed in a continuous length, without any splices or joints. The purpose of supplementary grounding electrodes is to lower the overall ground resistance. Common types of supplementary grounding electrodes include ground rods and ground plates. Supplementary grounding electrodes should be installed as close as possible to the equipment they serve. Equipment grounding conductors provide a path for fault current to return to the source. These conductors must be sized according to the size of the overcurrent protection device. Equipment grounding conductors should be installed in the same raceway or cable as the circuit conductors. Furthermore, consider the ampacity of conductors. The ampacity of a conductor is the maximum current it can carry without exceeding its temperature rating. The ampacity of a conductor depends on its size, insulation type, and installation conditions. Conductors must be sized according to their ampacity and the connected load. Furthermore, understand the requirements for conductor derriting. Conductor derriting is required when conductors are installed in close proximity to each other or in high-temperature environments. Derriting reduces the ampacity of the conductors to prevent overheating. NEC Table 310.15 specifies the derriting factors for various installation conditions. Also, recognize the importance of short-circuit current rating. The short-circuit current rating, abbreviated as SCCR, of electrical equipment is the maximum short-circuit current it can safely withstand. Electrical equipment must have a short-circuit current rating that is equal to or greater than the available short-circuit current at its terminals. The available short-circuit current can be calculated using engineering methods or obtained from the utility company. Also, know the requirements for selective coordination. Selective coordination ensures that only the overcurrent device closest to a fault opens, minimizing the impact of the fault. Selective coordination is required in certain applications such as healthcare facilities and emergency systems. In addition, be mindful of the requirements for arc flash protection. Arc flash is a dangerous electrical hazard that can cause severe burns and injuries. Arc flash protection measures include using arc-resistant equipment, wearing appropriate personal protective equipment, and implementing safe work practices. Arc flash studies can be performed to determine the potential arc flash hazard and to identify appropriate protection measures. And be familiar with the requirements for hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Electrical equipment installed in hazardous locations must be specifically designed and approved for use in those locations. The National Electrical Code, abbreviated as NEC, classifies hazardous locations based on the type and likelihood of the hazard. Consideration must be given to the importance of emergency systems. Emergency systems are designed to provide power to critical loads during a power outage. Emergency systems are required in certain types of occupancies, such as hospitals and fire stations. Emergency systems must be tested regularly to ensure they are functioning properly. The purpose of standby systems is to provide power to non-critical loads during a power outage. Standby systems are not required by code, but they can provide valuable backup power for essential equipment. Standby systems can be powered by generators, batteries, or other sources of power. Power quality refers to the characteristics of the electrical power supply, such as voltage stability, frequency stability, and harmonic distortion. Poor power quality can cause equipment to malfunction or fail. Power quality monitoring equipment can be used to identify and address power quality problems. Finally, remember to always prioritize safety and follow the National Electrical Code, abbreviated as NEC, and other applicable standards. Electrical work can be dangerous, but by following safe work practices and using appropriate equipment, you can minimize the risk of accidents and ensure the safety of yourself and others.